model, are they going to be like an AB configuration, or like is it going to be an AA configuration? So how is it going to be there?
Yeah, it's generally AA. Whenever there's lithium between the two layers, it goes AA on either side.
So it's like as soon as we add the first lithium in between two graphite layers, it's going to slide into AA.
I'm not sure if one lithium is enough. I think probably in the stage 1 prime, it's not AA.
Okay.
Yeah. I don't know whether all those details have ever been worked out and measured carefully.
Thanks.
Okay. Okay, so it's time to begin. So I will do that. I think I'll just change my video camera first, just hang on. Okay. Now, do you see my PowerPoint?
Yep.
Okay, great. So let's begin. Yeah, so I was talking about this path from a aromatic hydrocarbon to a graphite on heat treatment. And this is what happens when you have what's called a soft carbon precursor. A soft carbon precursor will allow you to make a pretty decent graphite. And the difference between a soft carbon precursor and what's called a hard carbon precursor is that a soft carbon precursor will melt and form a fluid phase somewhere in this temperature range between 300 and 500 degrees C. The formation of that fluid phase allows these flat aromatic sheets to line up parallel on top of each other. Okay. And if you don't go through a fluid phase, then however the carbons are bonded remains the way they're bonded, if you like, and you don't get easily forming flat sheets of graphene like this. So the point is that carbonaceous precursors fall into two classes, hard carbons and soft carbons. Okay, so like I said, soft carbon precursors like tar, petroleum pitch, anthracene, polyvinyl chloride, all pass through a fluid phase during heating. This allows small graphene sheets to stack parallel. Hard carbon precursors do not melt. By contrast, they retain the shape of the carbonaceous material before heating. Examples are wood, sugar, hardened epoxies, etc. This does not allow formed graphene sheets to stack in a parallel manner. So a pictorial example of this is actually best. So around 1995, we were making carbons from virtually everything we could. So this is a little disc of oak compared to a copper penny, okay? And then this disc of oak was put into a small furnace inside a sealed quartz tube and heated to 700 degrees C, all right? And after heating, all that happened to it was it shrunk. It obviously didn't melt because it still maintains its circular shape. And it shrunk because its weight reduced by about 70%. So it's about 30% of the original mass of the oak here. Okay, so if you want to know if something's a hard carbon or a soft carbon, just pyrolyze it and see if it shrinks and maintains its rough shape. I don't have a photo of it, but we also made a 1 centimeter cube of oak and did the same thing, and it turned out afterwards to be about a 0.6 centimeter cube, okay? So it just shrinks. It's incredible. It doesn't melt. Whereas a soft carbon precursor would melt in that process. So that's the main difference between the two. X-ray diffraction is a really good way to probe what's happening to the structure of the carbon as it goes from low temperatures like 550 degrees all the way up to 3000 degrees. And we're going to follow carbons as we heat them and look at their X-ray diffraction patterns, okay? And this is a really interesting paper which has a lot of results in it that you can take a look at. But I'll just explain what's happening here as we go along. So this is a part of the X-ray diffraction pattern. And this peak that you see in both of these patterns comes about from the parallel stacking of the graphite sheets, okay? And the width of this peak tells you how many sheets are packed, or excuse me, how many sheets are stacked in a parallel fashion. The narrower this peak is, the more sheets are stacked in a parallel fashion. And I'm going to switch to my document camera now so we can talk about that. So I think you should see my document camera now. Is it true?
Yep.
Okay. So there's something called the Scherer formula, and it relates the size of a crystallite to the full width half maximum of the X-ray diffraction peak measured in radians. And it's a simple formula where the angle theta is 1/2 the angle that I showed you in those diffraction patterns. It's the Bragg angle, not the scattering angle. Anyway, it doesn't matter the details. What does matter is what happens if you work this out for the X-ray patterns I showed you on the previous PowerPoint slide. So for the hard carbon precursors, which were in the right graph, the full width half maximum of the peak was about 10 degrees. 10 degrees. And because 57 degrees is 1 radian, 10 degrees is about 0.2 of a radian. And we use an X-ray wavelength of 1.5. The angle is around 25 degrees. That means theta is about 12.5, and the cosine of 12.5 is very close to 1. So if you work out this number, you get about 7 or 8 angstroms. 7 or 8 angstroms only. So what does that mean? It means that if spacing between carbon sheets is about 3.5 angstroms, when the peak is so broad, it just means there's a few of them. That's all. Just one, or there's 2 or 3 stacked in a parallel fashion. Okay, and then they go off at some other angle in some other way, you know, like this. Okay, so when the peak is really broad, it tells you there's not very many of them stacked in a parallel fashion. So X-ray diffraction is really useful for looking at this. I'll go back to the PowerPoint. Okay, I believe you should be able to see my PowerPoint now.
Yes.
Yep.
Okay, thank you. I always like to check because I don't want to just talk endlessly. Okay, so look at this hard carbon here. See this broad peak? Like the half width of this thing is massive. It might even be more than 10 degrees, right? You know, where does it begin? Way over here? Where does it end? Way over here? It's incredibly broad. This is probably just 2 graphene sheets parallel. And then as you heat it up to 1,000, you can see it gets a little narrower, but it's still really broad. By contrast, the soft carbon here is much sharper than the hard carbon peak. So let's follow this a bit more. So Hang Shi actually was my very first graduate student, and he wrote this paper which came out in 1993. What he did was create a theoretical model that allows you to calculate the diffraction pattern arising from disordered graphite, where you could tell the program how many graphene sheets were stacked in a parallel fashion, what the lateral extent of the graphene sheets was. So for example, go back here, what's the lateral dimension of the graphene sheets, all right? And the probability for turbostratic misalignment between adjacent sheets. And with that model, and just a few parameters, the ones I've described, you can match the X-ray patterns of carbons and then understand what's happening while they're being heat treated. So it's a really nice paper, very mathematical, but papers that follow from it that we use to interpret carbon structure as a function of heating are quite valuable. So here we are with a soft carbon heated to 550 degrees C. The data is the black and the dash is the theory, so it fits pretty well. So you see this broad peak from the parallel alignment of graphene sheets, and then you see some other bumps and wiggles. These come about from the in-plane structure of the carbon, all right? And they're broad because the lateral extent of the graphene sheets is very small. If you heat to 1200 degrees C, you can see how much sharper now the first peak is. And that's because there's more of these graphene sheets that are stacked in a parallel way. And if you take the half width here, I don't know what it is, maybe 4 degrees, and apply the Scherer formula, you could make an estimate for how many sheets are stacked parallel. And this very first peak that you see is starting to become more prominent, and that's because the lateral extent of the graphene sheets is getting larger. So now let's heat it more and see what happens. So now things become very interesting. When you heat to 2000 degrees C, this is on a logarithmic vertical scale. So the half width of this peak, it's about what, 40,000 counts? So the half width is 20, okay? 20,000 counts. The half width is here. So it's very sharp, and there's probably 200 or 300 parallel graphene sheets at this point, okay? And now you come along and there's this incredibly strange shaped peak. You look at it, it's sharp and then it decays. It's like a triangle almost, triangular shaped peak. This is called a two-dimensional diffraction peak. Okay, so what it means is, I'll go back to my document camera to describe what a two-dimensional diffraction peak means. Okay, I think you should be able to see my document camera again. Is that right?
Correct.
Okay. So here is a graphene sheet. It has a large lateral extent. Okay. If the next graphene sheet is turbostratically misaligned and also with a large lateral extent, and the next graphene sheet is also turbostratically misaligned and also with a large lateral extent, and so on. If they're all turbostratically misaligned, you get a two-dimensional diffraction peak. The reason is there's good order in one dimension. In 2 dimensions along the graphene sheet. They're stacked parallel, so that means you get the diffraction peak from the parallel stacking, but there are no 3-dimensional correlations at all because the layers aren't organized in a stacked AB fashion, the way they're supposed to be. So you can tell when you see this triangular peak with a very sharp, steep left edge that you've got big sheets and full turbostratic misalignment like that. Okay, what's this peak that's appeared? This peak is the second order diffraction reflection from the first one. Okay, so if this one is sharp, this appears. Now let's see what happens when we heat to 2850 degrees. So at 2850 degrees, the graphite is getting close. It's getting close to being pretty decent graphite now. And what do we have? We have a very sharp first peak. This is telling us about the fact that many layers are stacked in a parallel direction. Several hundred are perfectly parallel. And then, if you look carefully, you'll see a very sharp peak and then a little bump next to it. So what's happening now is you're starting to get the AB stacking of 2H graphite. If the stacking were perfect without any turbostratic misalignment, this second peak would be sharp and the first peak would be sharp, and there would be another little peak that would appear right there, and this peak would sharpen up as well. So this graphite probably has something like 10% of its adjacent layers in turbostratic misalignment, and the rest of them, the other 90%, are stacked AB roughly. So it's really fascinating the way the diffraction pattern changes and the way the carbon structure changes. So slowly, when you heat from 2000 to 2850, you have enough thermal energy to take these big graphene sheets and rotate them into AB stacking. And this is why you need to heat to such enormous temperature, because it's a big piece of graphite that's rotating into alignment. Okay, any questions about this? All right, I'll go on. So if you plot the layer spacing versus the heat treatment temperature, and this is for a soft carbon precursor, you see a behavior a lot like this, sort of a continual decrease from around 3.45 angstroms down to 3.35 angstroms. At this low temperature, all the sheets are in turbostratic misalignment, and their lateral extent is not very big. When you get to 2000 degrees, all of them are still in turbostratic misalignment, but their lateral extent is pretty big. It's contracted a little bit, not sure why. But then as you heat it more and the sheets come into AB stacking, the spacing in between the planes becomes smaller and smaller. And this is not a big effect, right? But you can use this to help understand, what temperature the graphite's been heated to. You can use it to reverse engineer to some degree if you so desire. All right, so now let's compare a soft carbon that can be graphitized at high temperature to a hard carbon, which cannot be graphitized at high temperature. So take a look. These have both been heated to 2000 degrees C. The left panel is on a logarithmic vertical scale. So the half width of the first peak is incredibly small. Maybe it's a degree, I don't know, maybe less. Whereas the hard carbon, you know, the half width is still sitting around 7 or 8 degrees here. So the hard carbon has had very little graphene sheets rotate into parallel stacking, just maybe 6 or 7 or so. And from this peak here, you know, it's triangular. It's triangular like this one, but it doesn't have a sharp edge. This has a very sharp edge. And the sharpness of the edge tells you about the extent, the lateral extent of the graphene sheets. So the graphene sheets are small and not very many stacked in a parallel way. Completely different. And then if you compare at 2850 degrees, a soft carbon to a hard carbon, like I mentioned before, the soft carbon is already about 90% of the graphene sheets roughly are in AB-AB stacking. Over here, you still have a triangular peak. There's no evidence of the second peak and this other hump that are telling you about AB-AB stacking at all. And the model would predict that virtually all the adjacent layers are still in turbostratic misalignment. And now we've moved to a logarithmic vertical scale, you know, because there are more parallel stacked layers, but it's nowhere near as sharp as the soft carbon precursor. So big difference between hard and soft carbon precursors. So if you pick things like wood or sugar or lignin or cellulose or coconut shells or coffee beans or whatever, things that are hard carbon precursors, you'll never make a decent graphite for lithium-ion batteries out of them. So I'll show you in a moment that these type of materials are crappy for lithium-ion batteries. Okay, any questions up till here? So let's look at a soft carbon precursor. This is something called mesocarbon microbeads. I'll give you a homework problem where you learn what mesocarbon microbeads are. They're a soft carbon precursor, and they're heated to 2300, 2600, and 2800 degrees C. And this is on a normal vertical scale, not logarithmic. And we're only showing part of the diffraction pattern, where the part of the diffraction pattern that changes a lot due to AB-AB stacking is apparent. So again, the dots are the data and the black line is the calculated diffraction pattern based on the parameters of the model. So this P that you see here, this is the probability that adjacent layers are in turbostratic misalignment. And this PT is the probability that if you have 2 layers in AB stacking, the next one will be a C. So it's not a random rotation between layers, it's just a stacking fault. Instead of going A, B, A, and back to B, it goes A, B, C. Okay. So these kind of things affect the diffraction pattern, and you can obviously calculate it very well if you get the parameters right. So when you heat to 2600, the probability for turbostratic misalignment is 21%, and PT is about the same. 2800, about 10% of adjacent layers are in turbostratic misalignment. Okay. Now you may say, what the hell? Why are you telling me all this crap? I don't care. Well, you should care. This is why you should care. So these are graphs that show the voltage versus lithium content curves for different soft carbon precursors heated to different temperatures, and also a natural graphite with a very small value of P. Now these curves have been shifted up for clarity by 0.1 volts, okay? So don't think the voltage actually goes up like this. It does not. They're all down around, you know, the same voltage as the one at the bottom. I just shifted them up so they're not on top of each other. And I think you can tell that the amount of lithium that you can put into the graphite gets less and less as the value of P increases. In fact, if you plot a graph of the capacity in milliamp hours per gram versus the probability for turbostratic misalignment between adjacent layers, you get virtually a straight line. And the different triangles and squares and diamonds are different soft carbon precursors. Okay, so one might be coal tar pitch, one might be petroleum pitch, one might be needle coke, I don't know. But you can see that they all follow the same trend. There's another really interesting thing about this graph. So you notice that the capacity with which, or the full amount of lithium that you can reach gets less and less and less, right? And it goes back rather substantially as P increases. But look at this bump. This is where the stage 2 phase is full. This bump remains in almost exactly the same position. It's the length of the stage 2 to stage 1 plateau that shrinks. Okay? So that's really curious. And this is why, you know, when we look at voltage curves, you can learn things. You can say, what the hell? This is, you know, and again, if you have any blood flow, you should be saying, what? This is weird. Why would it do that? And because I know you all have blood flow, I'm going to assign you a homework problem to figure this out. Okay, so the fact of the matter is, if you want to have a graphite with high specific capacity, you need to have a pretty low value of P, you know, around 0.05, 0.07, something like that, to get up in the 350 milliamp hours per gram range. Okay, any questions about this? Okay, there's one more observation you should make about this graph. If you put lithium in between every pair of graphene sheets to the maximum amount, 1 lithium for 6 carbons, you get 372 milliamp hours per gram. Okay. Look what happens if P is 0.5. Well, the specific capacity is about 185. 185 is exactly half of 370. So does it mean that you cannot put lithium in between adjacent graphene sheets that are turbostratically misaligned? That would explain this straight line, which has this particular slope. Any comments? Am I still on the air? Like, is there an audience out there?
Yes.
Okay, good. Anyway, you'll have a homework problem where you get to consider this issue of, does it mean that you cannot put lithium atoms between turbostratically misaligned graphene sheets? Just go back to my document camera for a minute. So here we are, okay? I've got two graphene sheets. They're in AB stacking. Maybe I'll turn one of them over. Okay, so there's a white one and this one. You put lithium in between. They just have to slide 2 angstroms. 2 angstrom slide to go into AA stacking, okay? Now consider a big graphene sheet that's rotated at some wacky angle. When the lithium goes in between, it has to go into AA stacking. Well, how much energy is that going to take? A massive graphene sheet all has to rotate at one time. The carbon-carbon bonds don't break. And I don't think it can happen. And that's why you see that very interesting graph.
Hi, Jeff.
Yeah.
What if, like, as you mentioned, if because angle, the misaligned angle is very large, so at this in this case, like even the lithium is hard to go to the A type of stacking. But what if it's at higher temperature? What if the intercalation is happened at a little bit higher temperature? Will that help the this? Or
I understand the question. The thing is that the temperatures that you need to cause these sheets to rotate during graphitization are temperatures over 2,000 degrees C.
I see.
So the kind of temperatures that we can access in the battery, you know, maybe we can go to 70 degrees, 80 degrees C. It's just so trivial compared to what you need to cause these things to rotate.
I see. That makes sense. Thank you.
Yeah. All right, so let me share again.
Does the angle of the misalignment have an effect? So if it's just a small amount of misalignment of the 2 sheets of paper versus a 90-degree misalignment, because those are all grouped together as a random average, right, in your probability of P?
Well, it actually turns out it doesn't matter what the angle is. As long as it's rotated something, you still can model the X-ray pattern. So we don't know what the angle of rotation is. And for this structure, every 60-degree rotation takes you back to where you were because it's a 6-fold symmetry of the graphene sheet. So the worst possible arrangement would be a 30-degree rotation, not a 90. Well, a 90 would be equivalent to a 30, actually.
Right, I see. That makes sense. Okay.
Yeah.
Thank you.
Okay, what am I sharing right now? I don't know. Am I sharing my document camera or my PowerPoint?
Document camera.
Okay. Okay, it should be the PowerPoint. Is that true?
Yep.
Yes.
Thank you. Okay, so now we get to a really interesting thing, which is the fact that lithium intercalates nicely into graphite, as I've been showing you. So this is the first lithiation and delithiation coming out, back and forth. There's some irreversible capacity due to reactions between the lithium and the electrolyte at the surface of the graphite, but don't worry about that for now. But if you try to intercalate sodium into graphite, it just doesn't go. You know, you try, it goes down to 0 volts, and you plate electroplate sodium on the surface of the graphite. So you get about 20 milliamp hours per gram, whereas with lithium you get 370 or so. So that's bizarre. Why doesn't sodium go in? Especially when you look at this. Potassium goes in. Potassium goes in, and it goes to a limit of Kc8. not LiC6. All right, but sodium doesn't go in. All right, so this is some work by Kamaba, a nice figure that he published in a paper just comparing lithium, sodium, and potassium. All right, and so this is a real puzzler. And many theoretical people have, tried to explain this, and I don't think any of the explanations are really very convincing. So it is what it is, and it's really bizarre. Okay, so that's talking about the carbons in region 1. Okay, so if you look at this curve, it's got the soft carbons that are able to get up to our 350, 370 milliamp hours per gram. And there's another curve here for hard carbons. Okay, and the hard carbons, because they don't graphitize well, and P is still large, they never give you any kind of reasonable capacity at all. Okay. All right, so now let's talk about these other carbons. Where does this huge capacity comes from in regions 2 and 3? Like, this is incredible. Okay, so this is a big, massive table. I might have an animation though. That's in one of the papers that we published long ago, and it talks about using a whole bunch of different precursors for making carbons. So there's Crowley coal tar pitch, there's Kariha pitch, polyphenylene sulfide, polyvinyl chloride, PVDF, and epoxy novolac resin that you would use to make epoxy. And all these things, you heat them at different temperatures. You measure their composition after heating because they all have carbon and hydrogen. As I mentioned before, the higher you heat, the larger the lateral extent of the graphene sheets get and the less hydrogen you have at the edges. So when you look at these, the hydrogen contents all drop. They all drop in every of these situations as the heat treatment temperature goes up. And this polyphenylene sulfide, of course, it starts with sulfur, so it has sulfur too. And if you plot the hydrogen to carbon atomic ratio, you can see that it goes down in all of these materials, all right? So then we also measured the reversible capacity in milliamp hours per gram for these things. There's massive numbers. And the first cycle irreversible capacity, there's also massive numbers, but there's no arguing that many of these things can reversibly react with tons of lithium. And what's going on? This is, again, showing what these voltage profiles look like. So this is for the Kariha pitch, heated at different temperatures. And these curves have been sequentially offset just so they're not on top of each other. The shifts are listed down below for the offsets. Not important. But what's really bizarre about this is you add the lithium, around 0.1 volts, but you can't get it out until up around 1 volt. This is called hysteresis. And if you look at this 1 volt plateau, it slowly goes away with heat treatment temperature, right? It's big, smaller, smaller, smaller. And if you look back at this table, you take a look at the full width of half maximum of the 002 peak, like the number of graphene sheets that are stacked in a parallel way. Like once you get up to 700 degrees, they're almost constant, 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 constant. They don't vary much. They don't vary much at all. And yet the capacity for lithium changes by a factor of 3, almost. So this drove us crazy because we were thinking, there's hardly any change to the carbon structure in this temperature range. Oh yes, and this LA is the lateral extent of the graphene sheets. It's not changing very much either. Change a little bit. So what's going on? Where is this extra capacity coming from that goes away? It drove us crazy. But the most important thing was noticing that it was present in all of these materials, regardless if they were hard carbon precursors, they had this high capacity, or if they were soft carbon precursors, they had this high capacity, etc. And finally, we plotted this graph. We plotted the reversible capacity versus the hydrogen to carbon atomic ratio in the material. Okay, and there's a pretty good correlation, and this solid line is 1 lithium per hydrogen. So for every hydrogen in the material, there's a lithium that can bond nearby. That's the thought. So I'm going to go to my document camera and explain what the thinking at the time was. Okay, so this is quite amazing. It's the only thing that correlates with the observation is the hydrogen to carbon ratio. Okay, so any questions about that while I'm going to my document camera to sort of draw a picture? Why can't I do that? Okay, you should see my document camera, is that correct?
Yep.
Okay, thanks, Saad. So here we are. We've got part of a graphene sheet at the edge like this. Okay, and I'm not going to draw it going off to the left. And, you know, these are aromatic rings. They're aromatic rings. So there's double bonds and single bonds in here. But the edge is thought to be, especially if you heat them in inert gas, the only thing that can be terminating at the edge predominantly is hydrogen. Hydrogen terminated carbon. That's why the hydrogen to carbon ratio is so big. Like those numbers I was showing you was in weight percent. So it's like three weight percent. And hydrogen is 1/12 the atomic mass of carbon. So 3 weight percent is a large atomic percent of hydrogen. So the idea is, you know, this carbon that you have here is it's an sp2 bonded carbon. And as you know, you can have benzene, very simple chemical, where all the hydrogen, it's a planar molecule, and everything here is sp2 bonded, aromatic. But there's another compound, which is sp3 bonded, hard for me to draw, but it's cyclohexane, and every carbon has 2 hydrogens bonded to it. So this is benzene. I'm not sure you can see my screen anymore. And this is cyclohexane. So the belief is that this extra lithium comes along and binds next to the hydrogen at the edge. And the carbons at the edge move from sp2 bonded configuration to sp3 bonded configuration. I can tell you that every time
You have no messages.
I can tell you that every time the structure of the host material changes in some way. So here, the local environment around this carbon changes from sp2 flat to sp3, tetrahedral bonding. Whenever you have a change in bonding of the host, there's hysteresis every time. Okay, silicon has hysteresis. Why? Because you start with silicon-silicon bonds. In silicon, you end with no silicon-silicon bonds left in the material when the lithium's fully reactive. Here, the host changes. You have graphite with regular intercalation. The graphene layers don't change at all. The lithium goes in between, and you have reversible intercalation and deintercalation. So if you go back to this, I think you should be able to see my slides again. Is it true?
Correct.
Look at this. At 550, you have a lot of hydrogen per carbon. Look at the voltage curve. Big hysteresis. Lithium goes in around 0, comes out around 1. The hydrogen content drops. The magnitude of this 1 volt peak gets smaller and smaller. And by 1000, when the hydrogen content's virtually 0, it's gone. So all of these materials in that big table on the previous slide, they all show the same behavior. The same behavior happens. It's got to be associated with the hydrogen in the material. And the point is, no matter what we tried to do, we could not eliminate the hysteresis, and we could not eliminate this very large difference between the first lithiation capacity and the first delithiation capacity. So that's called irreversible capacity, which is very bad. So these hydrogen-containing carbons turn out to be completely useless for lithium-ion batteries, even though they occupied the scientific community for a long period of time. Any more questions about region 2, if any? Okay, let's move on to region 3 then. What about region 3? Well, it's nice to look at the voltage versus capacity curves for the carbons in the different regions. So region 1 is graphite. You see the typical voltage curve with all the plateaus due to staging. In region 2, if you make a carbon that's been heat treated to about 600 or 700 degrees C, you get this big hysteresis loop, massive capacity. But to get here, you have a first cycle with big irreversible capacity, so not useful. But region 3 looks pretty interesting, right? The hysteresis is small. You get up to 550 milliamp hours per gram. It looks pretty good. And region 3 is found in hard carbon materials heated, well, it says about 800 and 1100, more like, I guess, more like 1000 and 1200 degrees C, you'll find this type of behavior. And if you look carefully at this voltage curve at the bottom, there's no bumps and wiggles here at all. It's just a smooth, flat curve. And then a sloping region. So there's a sloping region and a flat region. It's very different than region 1. And it's in a hard carbon, heated between about 800 and 1100 degrees. So what's going on here? This is a graph from one of Ed Buell's papers. Ed was a PhD student in the group back in the late 90s, I guess. And he's just showing you the difference between the first few lithiation, delithiation cycles of an industrial, at that time was used very much, a graphite that was used in lithium ion cells. You know, you've got your 300 plus milliamp hours per gram and small irreversible capacity, compared to sugar, just simple sugar heated in inert gas to 1050 degrees C. You've got this much larger reversible capacity. You've got bigger irreversible capacity, and you've got some tiny amount of this hump around 1 volt. This is shifted up by 3 volts for clarity here. And this is just from a little bit of hydrogen still remaining in the material. If you heat it higher, these two curves close together. So the question is, where is all this lithium being stored in this material? Like, what's going on? And, you know, imagine you or me and my students back in the early 90s, and you saw these 3 kinds of behavior. What do you think it would induce in us? It's a 2-word answer. Who knows what it is?
Is it blood flow?
It's blood flow. Right on. Good for you. Okay, so anyway, it's time to stop, and I'll continue next time with region 3, and we'll probably finish most of this negative electrode material work next time, and I'll start on the next topic. So I'll email you some more lecture notes and probably another homework in the next couple of days. Any questions about this part? Okay, hearing no questions, we'll stop for today then. I'll see you all later.